Hi, everyone. I'm Vikesh, and I'm going to talk to you today about non-additivity in quantum communication. Before I proceed, I said that in the abstract that no knowledge of quantum theory is required. So I will start with some basic ideas in both quantum theory and also some basic ideas in classical communication theory. And what you can expect from this talk is essentially a way of generalizing noisy classical communication using quantum theory. The ideas for this date back to a paper in '96 where Bennett, DiVincenzo, Smolin, and Wooters sort of laid down what the task of communicating information using quantum resources looks like. The other thing to expect from this talk is that I'm going to try and point out certain challenges and opportunities in quantum communication. By that I mean, in some sense, sort of both theoretical challenges and then again opportunities to contribute to the task of building this kind of theory of communication. Finally, I'm going to introduce what I mean by the term non-additivity in quantum communication. And then I will try eventually to get to a certain new result that we have, which is kind of a conceptual surprise about the transmission of quantum information. Viewed from the classical lens, this is a very different kind of result, which classically one would not expect. And perhaps another question to answer is why should one care about all of these things? One point of view is that, well, a theory that describes the world to the best of our knowledge is quantum mechanical. And once we have such a theory for describing physical systems, one would think that information which is encoded in physical systems is affected by this theory, and the transmission of information is affected by this theory. And so the theory of, say, the transmission of information might have some changes on the basis of what this theory has to say, or it might not. But it would be nice to know what the implications of this new, not really new, but of this sort of these laws of quantum mechanics have on the theory of information. The second is that, well, this theory of communication that I have been referring to for some time is under construction, which for researchers means that it's a fertile ground for exchange of new conceptual, theoretical, and numerical tools. And for that reason, it's at least worth looking at and knowing what sort of is going on in this area. Let me start, now that I've given you some advertisement for this talk, let me start by some basic ideas in classical information theory, which we sort of take for granted. The first idea is that of ordinary classical information. It's the kind of information that's stored in bits. For instance, if you store the outcome of an unbiased coin, this can be stored in a bit. And when this is stored, when you know the outcome, you know some information. And this is the idea of ordinary classical information. What we take for granted in such a case is that this information can be read without being disturbed and copied. So for instance, when I read a piece of paper, I usually do not disturb the information in that piece of paper. And if I take two pieces of paper, one blank and one filled with information, I can easily copy it without affecting the piece of paper that had written information. This changes when you move to quantum mechanical carriers of information. The example of a quantum mechanical object, or an object that is best described, whose properties are best described by quantum mechanics, is the polarization of a photon. Photon is a sort of a quanta of light. And this light has a certain polarization and which is best described by the laws of quantum mechanics. These polarization states could be, say, linear, and then they could be vertical or horizontal, and this describes two directions of polarization. And you can describe each direction by assigning to it a bit. And so if the photon is vertical, you say it's 0. If the photon is horizontal, you say it's 1. And this is two orthogonal directions, and these are distinguishable directions. So these photons can store classical information that way. But the same photons can have what are called circular polarizations. In these circular polarizations, again, you can have left circular polarization and right circular polarization. These are also orthogonal in that they can be distinguished and can be used for storing bits. But these polarizations are somewhat linear combinations of linear polarizations. So a circular polarization can be written as a linear combination of vertical and horizontal. This adds a sort of new dimension to this information storage device. In any case, the basic property that I initially referred to is that such quantum states can be written down, and these quantum states, which describe the polarization of a photon in this case, cannot be copied. So there's no particular operation here represented by U, which takes an initial quantum state here represented by psi inside this kind of straight line right bracket notation, which is called a ket. And I'll be using this, well, I'll be making minimal use of it, but here I've used it. And you start with the reference system, which initially is in some reference state here labeled as 0 and put inside this straight line bracket notation. And then there's no operation which can start with this psi and then copy it without having any effect on the original state psi for all possible psi. And so copying of sort of quantum information without disturbing it is impossible. Another aspect is that when you try to read this information, you end up disturbing it. This is a departure from the classical case. And to represent this sort of polarizations that I've been talking about, one uses a geometric picture. So if you want to look at this mathematically, a quantum state here can be mapped into a vector in R3, where antipodes, and a unit vector in R3 to that, where antipodes of a sphere represent orthogonal states. So in this case, I was speaking earlier of vertical and horizontal polarizations of a photon. In this case, the top of the z-axis of this sphere represents 0, is given by 0, and that's the vertical polarization. The bottom is a horizontal polarization. And then what I called right circular and left circular can also be called left diagonal and right diagonal polarizations. And these are represented by plus and minuses here. Another construction that has been done, this is for those who are mathematically inclined, is that I start out with these quantum states, and while I've represented them in R3, their mathematical description can also be done in the space of complex linear vectors, where the complex is two-dimensional. And so, for instance, the plus state here, which is a linear combination of vertical and horizontal, is written as 0 plus 1, and the square root of 2 is kind of a normalization that we use. And the minus state is 0 minus 1, and again, the square root is a normalization. These states are orthogonal in the sense if you take the inner product of these two vectors, you will get 0. And then I use another notation where a projector onto a state psi, which I write in this sort of mathematical way, in this sort of physics notation, is given by a square bracket with the label inside. Okay. Next, I want to move to a description of classical and quantum channels. So having described to you in the previous slide classical bits and their quantum analog, I want to now start with the classical description of a noisy channel. A noisy classical channel is a very interesting abstraction. whose physical description is as follows. It takes classical inputs, which are distinguishable. So inputs that are distinguishable. So for example, letters from an alphabet, A, B, C, D, from the English alphabet, all letters are distinguishable. This is mapped into some kind of box, and the box returns an output, which is also a set of classical symbols that are distinguishable. The way to describe a quantum channel is as follows. You take as input not classical distinguishable inputs, but quantum states. And you return as an output a quantum state. For example, you put a photon into a pipe and out comes another photon on the other end. And this describes a quantum channel. And what I just described, the photon going into and out of a pipe, is something that happens in the real world very often. Fiber optical cables have the task of sending photons from one place to another. The mathematical description to which I want to move next of a classical channel is as follows. It takes an input distribution over all its possible input symbols and returns a distribution at its output symbols. And these output symbols are connected linearly through a conditional probability. So you send in an input distribution, out you get is an output distribution. And the channel n itself is this conditional probability P of y given x in this sort of mathematical sense. In the quantum case, you do exactly the same thing. You take what is called the quantum generalization of a probability distribution, and you have a map that takes this probability distribution, the quantum generalization of the probability distribution, to an output, a generalization of a probability distribution. The way to mathematically write down this quantum generalization of a probability distribution is to look at positive semi-definite operators of trace 1. Let me remind you, a positive semi-definite operator is something that has positive eigenvalues. And when you say it has trace 1, these eigenvalues sum to 1, which means that the diagonal entries of any positive semi-definite operator forms a natural sort of classical probability distribution. And so there's a way to take any classical distribution and put it inside a quantum probability distribution simply by taking the classical distribution and putting into the eigenvalues of this quantum distribution. And this, so this is the way we describe a channel in quantum information. Next, I want to take you to a somewhat...
Excuse me, I have a question.
Yes, go ahead.
So we have this linearity constraint you mentioned in the classical channel. Is there an equivalent of that for the quantum channel?
Yes, there is an equivalent of that. This channel, which I've written by the calligraphic B, is a linear map. It takes the distribution rho x linearly to the distribution rho y. There's additional constraints that comes from physical principles, but so in the interest of say precision, it's a map that takes a dense positive semi-definite operator to a positive semi-definite operator, and if you take the tensor product of two positive semi-definite operators and apply the map to one of them, it maps the joint sort of tensor product operator to another positive semi-definite operator. So it's what are called completely positive trace preserving maps. Okay, so that's kind of the keyword to search for if you're looking for the precise mathematical definitions. But yes, the map is linear. In fact, the linearity shows up everywhere. Okay. Now I want to describe a task which to this audience might be somewhat more familiar than what I have been discussing thus far. The task is the communication of classical information using a noisy classical channel. So in this task, you have a channel N, which you use K times in parallel with itself, and you allow a sender, usually called Alice, to take messages that they have, and then you encode them through some operation into the input of the channel. And these channels now take the encoded input and map it to an output, which this output is then decoded by another person, Bob. And the task is the following. Alice is supposed to encode KR bits with vanishing error as k tends to infinity, where k is the number of uses. And if you're able to do that, then R represents an achievable rate of communicating information from Alice to Bob using the channel N. And the asymptotic capacity of this channel N is given by the maximum achievable rate R. And essentially the same idea can be generalized in the quantum setting. You replace the classical channel N in the previous picture with a quantum channel B here. You replace the encoding operations in the previous one written by E and D with quantum encoding and decoding operations. You replace the messages that Alice was sending by quantum states, and you replace the messages that Bob was decoding also by quantum states. And then the unit of quantum information per se is a qubit, just like the unit of a classical information is a bit. And you write down an analogous statement which says that if Alice is able to send KR qubits with vanishing error as k tends to infinity, then R is an achievable rate for noiseless communication or between Alice and Bob. And the maximum achievable rate gives the capacity of this noisy quantum channel. At this point, two additional comments on an order. Well, I initially said that these quantum channels are generalizations of classical channels, so they should be able to send classical information. And that is true, these channels can send classical information, and then you can define the capacities analogously as it is done in this picture. All you need to do is replace the term qubit here with a bit. And then you will have the asymptotic classical capacity of a noisy quantum channel. A second comment is in order, which is that you can send classical bits in such a way that, and now here's an additional idea, you can send classical bits privately so that someone who's sort of listening to what you're sending and by the act of listening adding noise to your communication channel cannot understand what you sent. So this is the task of sort of private communication. And there's a capacity which can be defined. Similarly, you encode and decode private classical bits with vanishing error. And then there's like a whole family of capacities that you can just define. You can assist your channel B with some other resource, and then you can say what's the capacity of this task, and so on. And so for each thing, you write down an operational task, and what you eventually want to do is compute these rates. And so let me go ahead and remind ourselves what one does to compute an achievable rate in the classical setting. The idea is to take a classical channel, which takes symbols in some alphabet X to symbols in some alphabet Y with probability P of Y given X. You define the following mathematical, what are called information theoretic quantities associated with probability distributions. You define what is called the Shannon entropy of a probability distribution Px by multiplying Px with its logarithm and putting a minus sign outside it and summing this Px over all possible x. You can also define what is called the mutual information between two random variables x and y. You take the sum of the entropies of the individual distributions and subtract from it the entropy of the joint distribution. And you then construct another mathematical quantity, which here has been referred to as the channel mutual information, but you may have seen it with a different name, and I will use that name shortly. You maximize this channel mutual information over all possible input distributions to come up with what I call the channel mutual information, C1 of n. And this is just a number at this point. The same kind of recipe works in the quantum setting with the proper quantum analogs. The proper quantum analog of the Shannon entropy of a random variable x with probability distribution px is the von Neumann entropy of a density operator, which is the quantum generalization of a classical distribution. It proceeds as follows. You take the density operator rho, which is a positive semi-definite trace 1 operator, multiply it with its logarithm and take the trace. Suppose rho is diagonal and its eigenvalues are px, then this will just give you the Shannon entropy. Otherwise, for a general density operator, you can always sort of diagonalize it and then compute the Shannon entropy of its eigenvalues. This will give you the von Neumann entropy. Interestingly, the von Neumann entropy was defined before the Shannon entropy. And the story goes that the idea to call what this quantity, which is now known as the Shannon entropy, was planted by von Neumann. Next is the mutual information of a classical channel, which I had defined, mutual information between two random variable x and y. The proper quantum analog of this is the coherent information in this case, which is that you have an input distribution, you take the von Neumann entropy rho A, it's mapped to some output distribution rho B, and the coherent information is just the entropy of P minus the joint entropy of A and P. And then the channel coherent information is just obtained by maximizing the coherent information over all input density operators. It is quite analogous to the classical case. Next is we have written down, okay, in the previous slide, we've written down now the channel mutual information, the coherent information. Each of these have been proven to be an achievable rate of communication in their respective settings. So the channel mutual information is achievable rate for sending classical bits. The channel coherent information is an achievable rate for sending quantum bits over a quantum channel. Now, yes.
The notation S of AB, that's not really a product. That's just shorthand for mutual for a joint distribution or something.
That's right. That's shorthand for a joint distribution. I've snuck in something which is complicated. So okay. Because rho A usually will go to some rho B, right? And then where is the joint AB state? There is some game there, but I've ignored it for now.
Okay. Thanks.
Yeah. Okay. Now I want to tell you that there's a recipe for finding the channel capacity now that I've given you a recipe for finding achievable rates. And this recipe for finding the channel capacity has been written in a somewhat unfamiliar form to those who are probably aware of classical information theory. It's written in such a way that the discrepancies in the quantum case come out clearly, and the things that we take for granted in the classical case are sort of pointed out clearly. One of the things we take granted is additivity. Well, we don't take it for granted, you can prove it. The idea is that this channel mutual information for two channels n and n prime used in parallel, and where I say the cross symbol implies that you're using the two channels together. The coherent information of this joint channel is sum of the mutual information of this joint channel, is the sum of the mutual informations of the individual channels. And the channel capacity can be written down as this kind of an asymptotic formula where you take k parallel users of a channel, compute its coherent channel mutual information divided by k, take this limit, and you get the channel capacity. It turns out because of additivity, this, which I pointed out in the previous line, this limit is trivial. The k just factors out and you can cancel them off and you just get C1, which is the channel mutual information. And this additivity in the first case also implies that the capacity of two channels used together is just the sum of the capacities of the individual channel. In the quantum case, all of this breaks down. So we have what is the non-additivity of the channel coherent information. So if you have two channels B and B prime used in parallel, where used in parallel, I have used this cross circle symbol called tensor product or Kronecker product. the coherent information of the joint channel can be greater than the sum of the coherent informations of the individual channel, and there are cases where this inequality is strict. As a result, the quantum capacity, which you just write down as an analogous limit, can now be strictly greater than the channel coherent information Q1. And in fact, a second level of non-additivity can happen where the capacity of two channels used in parallel can be greater than the sum of the capacities of the individual channels, and there are cases where this inequality is strict. Let me spend a slide re-showing you the same equations just to impress upon you how different this is from the classical case. The main idea is that two quantum channels used together can send quantum information at a higher rate than each channel used separately. And this is something that doesn't happen in the classical case. And let me take a pause here and answer some question that you might have. Is this something weird about just quantum information that you're trying to send, that it's this kind of non-additivity works out? What if I try to send classical information using a noisy quantum channel? All this is go ahead. Are these non-additivities still present? The first non-additivity is known to be present. The second non-additivity is not known to be present. And so that's an open problem at the moment. So the point is that these non-additivity somehow, yes.
Sorry, I got lost in the Q1 and Q. Is the Q this limiting?
Yes. So the Q is the ultimate capacity of the channel. It's the maximum achievable rate. Q1 is a specific achievable rate. And this specific achievable rate is essentially obtained by generalizing Shannon's argument for computing a lower bound on the achievable rates. Okay, good. So both these things can be non-additive. And as a result of this non-additivity, several questions become hard. So let me remind you, the quantum capacity is the limit of these Q1s, and it's the maximum achievable rate of sending quantum information.
What was the open question? I thought the open question was that the Q could not be greater than strictly. What was, you mentioned an open question last time.
Yes. So let me remind. So the open question is as follows: use a quantum channel to send classical information. At the moment on the screen, I have written down equations for sending quantum information across a quantum channel. And then ask the question, is the capacity of two quantum channels used together greater than the capacity of the sum of the individual channels, where the capacity is of sending classical bits? That question is still open. Did I clarify?
But for qubits, both these inequalities are known to be tight.
For qubits, both these inequalities are known to be loose, in the sense the inequalities can be strict.
Right. Sorry.
Yeah.
I have a quick question. So what if you send classical information across the joint channel, but quantum information individually? What happens to these inequalities in that case?
You send classical information across a joint channel and quantum information across the individual channels. So there's 4 channels in play.
Oh, you can assume that they're the same, right? Like just.
Oh, you want to simultaneously send both classical and quantum information?
Oh, I just want to understand like what the inequality is if you consider this model.
Actually, I don't think I know the answer to that one. Yeah, I don't know what happens when you. Well, trivially, I think if you're sending classical information, you could use a channel which has no ability to send classical information, and then you'd be just left with the quantum part, and then you trivially get that the quantum inequality holds. So in that sort of appended setting where you're sending both classical and quantum information across several channels, just the quantum part will give you this non-additivity per se. But that's kind of a trivialish statement.
Thanks.
Yeah. Okay. Yes. So what happens because of this non-additivity? Well, a central question, of course, is if I give you a noisy quantum channel and I ask you, can I send any quantum information using it? The answer is in general hard to find, because there is this kind of interesting example where you compute these Q1 rates for sending qubits, and they are 0 for n parallel uses when evaluated for n parallel uses of the channel. So Q1 of B, and then I have used a subscript tensor n. So this indicates n parallel uses of the channel B. The current information of the channel evaluated here is 0, but you add one more channel and the current information becomes positive. So if you look at the limit on the top equation, you can evaluate any first k terms of the limit, and you will get all zeros, and the k plus 1th term will be positive for any k greater than 1. And so it subsets the problem of computing the capacity itself seems horrible. And I think there's an open question here as well, which is that is the capacity even computable, in the formal sense computable? And I don't think the answer to that one is known. Next is a somewhat interesting question. Suppose I tell you the capacity of a channel is 0, or you have been able to find it using some means. Is this channel useless for sending quantum information? The answer to that one is also no. You can take two channels which individually used, even if you use them asymptotically many times, can't send any quantum information. But when you try to use them together, they can be used to send quantum information. This is the so-called superactivation of quantum capacity. And so two channels that can't send information separately can be used together to send information. And this is a somewhat bizarre effect, which one wouldn't expect in classical information theory. The idea being, if you have two classical channels that can't send any information, if you use them together, they won't be able to send any information. Somewhat intuitive and well-established result. But in the quantum...
That's kind of like a classical channel, which you have a pseudo-random number generator XORed with every bit. And then with one channel like that, there's no information can get through. But if you have two channels, then you can by XORing them, you get the XOR of the data. You see what I'm saying?
I understand what you're saying, but that's different from doing different from using them together. So the noise somehow is being correlated in the channels, right? So you do XOR twice on the same input.
Yes.
And
not the same input. Even if it's different, you can still get information statistically about the two different streams of bits. But anyway, I guess it's a different thing, I guess, than what you're doing.
It's slightly different, yes. It's different from using them in together, right? It's different from using Skype and a phone connection together. Each of which is noisy, for instance. Because but I didn't know this. This is an interesting fact that the XOR works this way and can be thought of in the channel perspective. Okay.
Vikesh, maybe a different way to phrase that idea is a classical channel with a secret, like, internal working can also have this property.
I see. I see.
If I can't examine how the channel works, I can still send information if I have two copies of it. But if I only have one copy, I can't send any information if I don't know how it, if like there's certain things I don't know how it works. Like if it's a one-time pad channel, I can't send information through a single one-time pad channel.
Right. So, I mean, I guess this is turning into discussion, but somehow I want to discuss a little further, but perhaps at the end of the talk.
Sounds good.
Okay. All right. So I pointed out these non-additivities cause some issues, namely computing the capacity or checking that it's positive becomes hard. So you might ask when and why are these current informations and channel capacities non-additive? Answer is, I mean, not much is known, but there are some examples and so on. And so this is where we have sort of a scheme for giving sort of a mechanism or one possible mechanism which can give rise to both capacity and non-additivity. The basic idea is somewhat simple, so let me try and get it across with some equations in. Think of a positive semi-definite operator rho, which has trace 1, and it depends on some parameter epsilon. I call this rho of epsilon. It has a von Neumann entropy, which can be written in terms of the eigenvalues of this density operator, lambda I, and I've written them in this equation. Now, assume that there's only two eigenvalues in play, the rest are 0, and they are epsilon and 1 minus epsilon. Notice if I take the derivative of this entropy, you will get an O of log epsilon term for small epsilon. And this I call a logarithmic singularity in the von Neumann entropy. And then, in general, you can have these logarithmic singularities if one or several eigenvalues of a density operator is sort of increase linearly in epsilon from 0 to leading order in epsilon. And then the key idea is that you can use these or analyze these, how these singularities appear in various places, and using, just by analyzing them, you can check if a channel has positive coherent information and has positive quantum capacity. And you can also check in certain cases if the coherent information Q1 is non-additive. I will spare you the precise procedure, the inner workings, but give you an example of sort of where these things can creep up. And so let me take an example of what in the quantum world, or what we call the incomplete erasure channel. Let's first look at the complete erasure quantum channel. It either sends the input density operator perfectly, or traces out the input density operator and sends a flag. The flag indicates erasure. And now suppose that instead of sending a flag that indicates erasure, you send something that nearly destroys the input density operator, but not completely. And that near sort of damping or near complete erasure is represented here on the top equation by C1. So if C1 of rho is just a flag state independent of rho, then it's an erasure. Otherwise, if it's sort of massively damped, for example, then it's what we call an incomplete erasure. These erasure channels have interesting channel capacities on their own. For instance, if you have a classical erasure channel, as long as the erasure probability is not 1, you can use them to send classical information. In the quantum case, if you have a quantum erasure channel, if the erasure probability is 1/2, then you can send quantum information. But the moment the erasure probability is greater than 1/2, you can't send any quantum information. And we think about a kind of specific kind of noise C1, where P is it damps the input state with some probability 1 minus P. So when P is 0, it damps the input perfectly, and so it does the same operation as an erasure. But for a slightly larger P, it does not completely erase the state. And I've put a big plot in front of you, which is what physicists do. The idea is, let me try and focus your attention to this cyan colored P equal to 0 line. It represents the P equal to 0 case, complete damping, it represents the quantum erasure channel, which has this weird property that when the erasure probability is greater than a half, it can't send any quantum information. In our case, the erasure probability has been flipped. Lambda in our case represents the probability of perfect transmission. So when the probability of perfect transmission is less than a half, the channel cannot send any quantum information. And that's what the magenta line does. Now you make P a very small number. Here I've written numerically 0.05, but it can be any epsilon positive. Turns out if you analyze these logarithmic singularities properly, you find out that the coordinate information is positive for all values of positive lambda. So as long as you don't completely erase, but send some amount of information in, you can sort of boost the entire parameter region with finite channel capacity. But the value of the boost is very small if you look at just the coordinate information. So on the top inset, I've changed various values of P and plotted on the logarithmic scale the value of Q1. And if you look at its logarithmic of Q1 divided by 100, and the y-axis is minus 5, 10, 15. So Q1 is e to the minus 500, for example. So the capacity is extremely small. So you won't detect it numerically if you sought to see it. But it is present, and it's present because of these logarithmic singularities. Okay, so that is one example. Then that was the specific example. There's a more general theorem, but you can prove of which that specific example is a special case. You think of a channel B, which has input dimension dA and output dimension dB. Whenever you have a quantum channel, there's some noise, and you might ask where this noise is coming from. This noise comes from an environment which interacts with the channel, and some information inadvertently always leaks into this environment. And it's this leakage that usually is the cause for a depletion in the amount of quantum information you can send. And here I explicitly write down that environment channel C, and I say that the environment has dimension DC. And then the theorem is that if the output dimension is larger than the environment dimension and some pure state goes through a rank DC output, then the coordinate information is positive. It's a kind of lot there in the theorem, but if you kind of compress it to some case like, so if the compression is the following. Suppose the input dimension is non-trivial, greater than 1, and the output dimension is large, so it's greater than dA times DC minus 1. Then the channel always has capacity. There is no comparable prior results to this to which one should compare, because I don't think there's an analysis of when the channel capacity is positive purely on the basis of the dimensions of a channel. And so the result sort of stands out from previous work in that sense. But there is previous work on fixed dimensions dA, dB, and that previous work can be recovered. So if you put dA in dB2, which has two-dimensional input, two-dimensional output, and the noise is characterized by a dimension 2 or greater, then you always can send information into the environment, which is another odd kind of thing. Okay.
Sorry, just to clarify, is this environment channel C, is it well defined from the description of the channel B?
That's an excellent question. Up to there is some freedom usually in defining this channel, but it is sort of unique up to what the physicists say a change of basis. So,
that makes sense.
Yeah. Okay. Next, I want to say what this log singularity approach says for non-additivity. Again, I have supplied you with very little details, but the idea is that you start with a channel which has 0 quantum capacity, can't send any quantum information through. Use it in parallel with something, and then the joint channel has positive coordinate information. That's kind of the non-additivity result. which is represented in equation 1. And again, this non-additivity result can be found essentially by analyzing how these singularities crop up in various places. Okay. And actually, with these two results, I think there's some follow-up questions which go in the following direction. One is to sort of analyze this dimensional arguments further. What range of output dimensions and environment dimensions can you have positive coordinate information? And then sort of a somewhat less concrete question is that, which are the zero quantum capacity channels which can nonetheless assist quantum communication in some way? They can't send anything on their own, but you know that there is this non-additivity, and you think you can leverage this non-additivity, or you can use this quantum zero capacity channel in some way and get something useful out of it. And so when can you do that? For what class of channels can you do that? So that's another question. And then this is something of more of a physics style thinking, but perhaps pervades. It's like, is there some intuition, like some principle that you could somehow sort of crystallize out and say, this is the principle which dictates when you can and cannot send quantum information, just so that we have some intuitive idea of what this information is? Because as I started at the beginning, this is some information that gets destroyed when you see it. You can't copy it without disturbing it, and it can be transmitted in these weird ways. Can one flesh out some principle that helps us better understand what is happening to this kind of information? Okay, with that, I come to a close for what I had planned to say. And we can pursue questions that people may have, because there's many things that perhaps I brushed aside or didn't explain clearly, or just as some people wish to talk.
Thanks, Vikesh. I had a question.
Yeah.
So if I took a standard classical communication channel,
Yes.
and I thought of it as a quantum channel,
Yes.
it would have zero quantum capacity.
Zero quantum capacity, yes.
But it would break. Would it break additivity? Like, can the combination of a classical channel with a quantum channel transmit more quantum information than?
So I think the result there is that forward classical communication doesn't help quantum capacity.
Okay, so
Yeah.
we have some examples. So
Yeah.
I guess a way to formalize that second question you put up would be, for which classical channels with which zero capacity quantum channels does there exist some quantum channel for which, the combination of the two can transmit?
I see. Given a classical channel, give me a class of quantum channels.
No.
That
Just given a quantum channel.
Given a quantum. I see.
There's the question, given a zero capacity quantum channel, like,
yes, I see.
does there exist any quantum channel that it can aid? Let's call it.
That's correct, because the extreme case, if the quantum channel is essentially a classical channel, then we know it doesn't. Right. Then there's another extreme case that there's some quantum channel which zero capacity, which can assist some channels. What happens in the middle? How do you connect the two?
Sure.
Extremes. Yeah, that's an interesting line of thinking. Yeah. Thank you for that comment.
Yeah, thanks for the talk.
Hello.
Hi.
Yeah, I had some, just a question on, are there any results like undecidability of computing these things known? Because, there is some striking parallel to Shannon capacity of graphs, where also you have these super additivity, but of course you don't have things like jump from 0 to positive like this, but there are basic things we don't know on what's the complexity of computing the Shannon capacity of a graph. Is there anything known given a channel?
Yes, so I think the question is open whether computing the capacity is decidable or not. As to what the complexity of answering such a question is, I don't think there is, except for some kind of trivial algorithm for computing the capacity, which is given by this limit, to the best of my knowledge, no alternate algorithm or even sort of way of giving complexity. And I guess the size of the problem is perhaps decided by the size of the input of the channel and the output. So the description of the channel. Short answer is complexity of computing capacity is wide open.
Okay. And related question to that is that in the Shannon capacity of graphs world, there is this theta function which gives an upper bound. I mean,
it's just the Lovaas theta function, yes.
Yeah. So are there any interesting upper bounds for quantum capacity?
Yes, there is a cottage industry of producing upper and lower bounds on quantum capacities. It usually has a somewhat semi-definite programming flavor. And so there are a large number of upper and lower bounds. And it's an ongoing race to show, I mean, none of them work properly for everything, all channels. In fact, for a given channel in different parameter regimes of noise, certain bounds work better than others. And so there's a quest to find sort of better and better bounds. And this, yes, so there's a lot of work in that direction.
Okay, thanks.
Yeah. Perhaps another direction worth mentioning is that capacity achieving quantum error correction codes are also somewhat of there isn't much there either. So can you write down an error correcting code that achieves capacity, even when the capacity is known? I don't think the question is fully answered, even from the quantum error correction point of view. Okay. Yeah, thank you for the question.
I have a question.
Yes.
Does the this issue of these codes, does this have anything to do with the problem of building a quantum computer where in order to deal with leakage or noise, it requires some kind of error correction in the algorithms or in the implementation of the quantum computer itself? Is that related?
That is correct. So that's correct. So the short answer is yes, there's a connection, and there's a strong connection. The idea, the way the problem has been posed here, it's somewhat asymptotic. But in general, you usually have some finite number of quantum systems to play with, and each of these systems has some noise, and you would like to design error correcting codes such that you can sort of still send information properly in the presence of noise. And so any quantum circuit which implements some kind of algorithm can be seen as a quantum channel. And so if you want for that circuit to work properly, given the presence of noise, you want error correcting codes, and the capacity gives an upper bound on the best possible error correction scheme you can have. And so in some sense, the quantum capacity question is also a question about quantum error correction. How well can errors be corrected? And these errors crop up in physical devices that people are trying to build. Yeah, so in some sense, it's the same question. Yeah.
Thank you.
All right. Well, that seems like everything.
Okay.
So thank you again, Vikesh. Thanks for the talk.
Thank you very much for giving me the opportunity to speak with you. All right, everybody. See ya.
Thanks, Vikesh.
Thanks, Ryan.